Hi, this is going to be 2C-2. We are talking about logarithmic functions. This will be a video lesson broke into two different videos. We're going to first talk about transformations of logarithmic functions, and then we'll talk about characteristics of logarithmic functions. So, without further ado, we are going to go ahead and learn about the characteristics of the graphs of logarithmic functions. And this video will specifically focus on being able to identify transformations using parameter values. So, without further ado, let's jump in, and we need to go ahead and review our properties. Properties of logarithms are so huge, and the good news is really there's three main players. One, we have the power property. Just know that if you have a power in your argument, you can move it out in front as a coefficient and multiply times that, as well as vice versa. If you want to go ahead and take a coefficient, you can move it up into the argument. Then these two generally will, one or the other usually appear. It's rare that they both appear, but they can, where we have the product property and the quotient property. If I am adding two logarithms with the same exact base, log base b plus log base b, I can multiply their arguments. A times x. Now note, it is possible, and what we can do is we can separate these. So if I have a product of two values and I can simplify, I can go ahead and undo that process. Now the same with the quotient property. If you have the same base and this time you are subtracting those logarithms, you divide the arguments. So notice that it is x divided by a, right? Your first value divided by the argument of your second value, okay? So let's go ahead and look at equivalent transformations. In AP Precalculus, we will go ahead and look at logarithmic expressions, and we're going to use our properties in order to identify equivalent transformation. So if I go ahead and raise an input of a logarithmic function to a power, that is equivalent to a vertical dilation of the function. You can see that power, right, for a logarithm, I can move it out, and now it's a coefficient. So this would be a vertical dilation. A horizontal dilation of a logarithmic function, when I multiply by k here, this is equivalent to a vertical translation. Again, if I multiply by a b value here, or this time they're calling it a k, I can separate these using the product property. So I'm going to be adding log base b of k. And then finally, change of base property. If I have log base b of x and I change the base, this implies that all logarithmic functions are vertical dilations of one another. For example, if I have log base 2 of x, consider the following function. G of x is equal to log base 8 of x, which is log base 2 of x divided by log base 2 of 8, which log base 2 of 8 is actually 3. So this ends up becoming 1/3 log base 2 of x. And using the change of base property shows that a vertical dilation of f of x by a factor of 1/3. Okay? So just to go ahead and remind you, the transformations, here are the parameters. If you have a logarithmic function, f of x is equal to a times log base b of c times x plus k. So if you have an a value, those are vertical dilations or reflections. Your horizontal dilations come from this c value here, and remember that we always take the reciprocal of that value. And then k, we can shift our function up or down, and that's your k value. Okay? Since the additive transformation f of x plus h, where h is not equal to 0, of a logarithmic function does not have proportional inputs, we're not going to consider horizontal translations of the lesson. All right, let's go ahead and look at some examples. The graph of f of x equals log base 2 of x is shown in the figure. Graph g of x equals log base 2 of x cubed on the same plane as f. What are the transformations of g of f? So what we're going to go ahead and do is I'm going to take log base 2 of x to the power of 3, and I'm going to take this power 3 and I'm going to multiply. I'm going to pull it out front. So this is the power property. This is the power property. And so what we have here is a vertical dilation by a factor of 3. Okay, and that's pretty much it. Okay, so when I use raise of power, that's equivalent to a vertical dilation there. Okay, B, graph h of x equals log base 2 of 4x on the same plane, xy plane as f. What are the transformations, or what transformation is h of the graph of f? Okay, so for this one, again, log base 2 of 4x, I'm going to separate these. I have log base 2 of x plus log base 2 of 4. So you can see that I just used the product property in reverse to separate this, and what this ends up simplifying to is log base 2 of x plus 2, right? 2 to the power 2 gives me 4. So what this is this is a vertical translation. Vertical translation up 2 units. 2 units. Okay? And so just going ahead and showing these here. Here are the graphs, right? So g of x, and then this is h of x. So you can see g of x here, graph of g, that's a vertical stretch by a factor of 3 compared to f. And then for h of x, you can see h of x here, it's shifted up. It's shifted up 2 units. Okay, C, graph j of x equals log base 4 of x on the same plane, xy plane as f. What transformation is j of the graph of f? Well, f is base 2, so again, what I need to do here for j of x, which is log base 2, log base 4 of x, I need to make it log base 2, and we do this with change of base. So this is log base 2 of x divided by log base 2 of 4, and log base 2 of 4 is 2. So I have 1/2 log base 2 of x, and this is a vertical dilation. Okay, last one. Graph k of x equals log base 2 of 1 over x on the same plane as f. What transformation is k of the graph of f? Okay, again here, k of x, I have log base 2, 1 over x. I'm going to use the negative exponent property to make this x to the power of negative 1. And then that negative 1 I can go ahead and bring out front. So log base 2 of x, and there you go. And what this is a vertical reflection. We have a vertical reflection across the x-axis. Okay, so again, that's the power property in play here. And again, you can see these. So k of x is here in the purple, right? That vertical reflection, and then the vertical dilation by factor 1/2 is j of x. You can see how that is compressed. Whew! Okay, so now that we've done that, let's go ahead and look at some multiple choice questions, which is where these types of questions will appear on the AP Precalculus exam. Go ahead, let's look at these, pause me, and then I'll talk through the solution here. Okay, so here's our first one. The function g of x is equal to log base 8 of x to the power 4 is equivalent to what transformation of f of x equals log base 8 of x? Pause me, show you the answer here in a second. Okay, this one is straightforward. You take that power of 4 and we can pull it out front. This is a vertical dilation by a factor of 4. And again, they tell you, hey, it's a transformation of what? Of log base 8 of x. Well, you want log base 8 of x to be by itself. So really, I have to use a property to remove that 4, to change this, right? So power property allows us to pull it in front. Okay, next one. The function g of x equals log base 2 of 4x is a horizontal dilation of the function f of x equals log base 8 of x. This is equivalent to what other transformation of the function log base 8 of x? And I think there is a typo here. I think this is supposed to be an 8 right here. So make that an 8, okay? So pause this, I'll go ahead and show you the answer. Actually, based upon the answers here, I think the typo is here. I think this should be log base 2 for these. Those should be log base 2. So please change those and pause me, try these. Okay, hopefully you got D, a vertical translation by 2. We can take the argument 4x and split it into 2 logarithms, log base 2 of x plus log base 2 of 4, which is 2. So we're shifting up 2 units. Okay, next practice one here. The graph of g of x equals log base 9 of x. It is a vertical dilation of f of x equals log base 3 of x by what factor? Okay, go ahead, pause the video, try this one. Okay, answer is D again. 1/2 is the vertical dilation factor because I use change of base on log base 9 to make it log base 3 because that's what they want for what factor is a vertical dilation of log base 3. I have log base 3 of x over log base 3 of 9, which log base 3 of 9 is 2. Because it's in the denominator, that is a factor of 1/2. It's like multiplying by 1/2. Okay? All right. Last practice problem here. Go ahead, pause this one. The function g of x equals log base 5 of 1 over x to the power 6 is equivalent to what transformation of f of x equals log base 5 of x? Remember, you want to manipulate this function to look like this function and then identify what is the parameter and what does it do to a graph, okay? All right, try that one. Here's the answer. Okay. For g of x here, I'm going to use the negative exponent property to move that x back into the numerator. Now my power is -6, and we can use the power property to pull it out front. -6 times log base 5 of x. Answer C. All right. So hopefully in this video you learned about transformations of logarithmic functions and how changing a function has an equivalent transformation in it. Okay. We'll go ahead in the next video, we'll talk about characteristics of a log function, such as domain, range, concavity, rate of change, and end behavior. All right, see you in the next video.